Okay, so we talked about a couple different bonding theories so far. We talked about the Lewis model, the Lewis theory based on Lewis structures. We talked about valence bond theory and also orbital hybridization. And both of these theories have their pros, have their cons. They both have been able to explain some of the properties of the elements and the molecules specifically we've seen so far. However, neither the Lewis theory nor the valence bond theory and um, orbital hybridization are able to explain some of the other characteristics of different molecules. And a good example of this is in the case of uh, diatomic oxygen or O2, which experimentally has been shown to be paramagnetic, right? So this is what has been observed due to, scientists doing experiments, etc. Uh, Oxygen, diatomic oxygen, does exhibit this property, and as a result, uh, oh, if you remember, paramagnetism means that there's at least one or more unpaired electrons in that species. So both the Lewis model and valence bond theory show that oxygen O2 has all of the electrons paired up. So this does not, neither of these theories are able to explain the paramagnetic nature of O2, of the oxygen molecule. So there needs to be another model to help explain what the observed phenomenon is with oxygen. And this is where there are a new model now known as molecular orbital theory, or sometimes known as MO theory, comes in. This is a much more robust model that helps explain virtually all of the characteristics of molecules. We don't use it very often because what we normally use is the simplest. We choose to use the simplest model to describe some of the characteristics. When those models don't work, then we go to um, the next detail model to explain observed phenomenon. So the model of molecular orbital theory is what we're going to use. We're going to talk a little bit about that now. It is going to help describe the paramagnetism of oxygen, of O2. And again, paramagnetism means that there's at least one unpaired electron. Okay, and in contrast, remember diamagnetism means that these are, in contrast, instead of being attracted by a magnetic field, diamagnetic species are weakly repelled by magnetic fields, and diamagnetic species contain paired electrons, right? So all the electrons are paired up with other electrons. So, what's the basis, what's the idea behind MO theory? Well, according to MO theory, the atomic orbitals are going to combine to form new orbitals that are now that are going to belong to the entire molecule as opposed to a single atom in that molecule. Okay, so the name itself actually tells you what it's about. We're looking now at taking atomic orbitals from the atoms that make up the molecule. We're going to combine them to form orbitals that belong to the entire molecule as a whole, right? So these new orbitals that we make are known as molecular orbitals or MOs. The molecular orbitals are going to have very, very similar characteristics to both the atomic and the hybrid orbitals. They're going to have particular shapes associated with them. They will also have different energies associated with them as well. Just like with regular orbitals, there will be a maximum of 2 electrons in each orbital. We're going to fill the molecular orbitals in the same order by which we fill other orbitals. We're going to follow the alpha bar principle, sticking them in with the lowest energy level first, and then we're also going to follow the Pauli exclusion principle and Hund's rule and all the other rules that we use to fill atomic and atomic orbitals. We're going to use the same rules for filling in our molecular orbitals. And the other thing that we're going to see is just like we saw in the hybridization, the number of molecular orbitals that we get out is the same as the number of atomic orbitals that we put in. Okay, so let's rewrite that. The number of atomic orbitals in, or put in, is equal to the number of MOs that we get out. So if we combine two atomic orbitals, we're getting two molecular orbitals. If you put in four atomic orbitals, we're going to get out four molecular orbitals, and so on and so forth. So let's take a look at the simplest example of where this can happen, and that is in H2, the hydrogen molecule, which is the simplest, the smallest homonuclear diatomic molecule. Homonuclear here just means that they contains the same atoms, right? Which in this case will be two H's, two hydrogens. That we are going to combine. According to the valence bond theory that we talked about before, if I have a hydrogen atom on one side with one electron, I can have another hydrogen on the other side with one electron there. These then can come together and they can overlap their atomic orbitals, because we have an H and an H, and then we have the overlap here, which we've talked about. And that's according to the valence bond theory, right? The overlap of the 1s orbitals leads to the formation of the bond between one H and another H. According to MO theory, the hydrogen molecule will form when the 1s orbitals actually combine to give molecular orbitals rather than overlapping of orbitals. Now, the thing to keep in mind is that when we, according to what we learned earlier on with quantum mechanics, right, our orbitals we can consider as waves, and these are going to have similar characteristics that waves do. They're going to have constructive and they're going to have destructive interference. And this is the way that these atomic orbitals are going to combine in a constructive way and also in a destructive way, combination of the atomic orbitals. Okay, so what's the difference between constructive combination and destructive combination? So a constructive combination is where the two 1s orbitals leads to the formation of an MO, a molecular orbital, that lies along the internuclear axis. That means it lies between both hydrogen nuclei. Okay, so if I have a hydrogen atom over here with its nucleus and another one over here, this nucleus, this new constructive combination will lead to the new molecular orbital being in between, sort of like so, between both of the nuclei in the hydrogen molecule, right? So we have here a good example of this, a much more better depiction of what I just tried to draw. So constructive combination increases the electron density between the two nuclei. So right here in this region is where the electron density is the highest. And again, that's what's going to happen in this constructive combination. This particular molecular orbital, this MO, is referred to as the bonding MO, right? And it's bonding because our electron density is highest in between the atoms, in between the nuclei. So if there's constructive combination, that means there needs to also be destructive combination, right? Because those are the properties of waves, of the wave functions and everything else we talked about, a few sections ago. Destructive combination leads to the 1s orbitals give rise to the molecular orbital that does lie along the internuclear axis, but it does not lie between the nuclei. Instead, what this does is the electron density here pulls the two nuclei in opposite directions. So in the case of destructive interference, which is the second depiction here, okay, the electron density is on the outside, right? Not in between. It's still along the internuclear axis like this here, the dotted line in between them. Okay, in the case of the bonding MO, the electron density was in the middle. Here, the electron density is on the outside. So instead, this is known as a destructive combination, and we refer to this type of MO here as an antibonding MO. Okay, so we put in two, so we input, in other words, two 1s atomic orbitals, and then the output that we get when we combine those is we get two molecular orbitals. Okay, one of them is a bonding orbital, a bonding MO, and the other one is a antibonding MO. Okay, just like we saw with orbital hybridization, it's a similar theme here. The only difference now is when these orbitals combine, the resulting molecular orbitals belong to the entire molecule rather than a single atom. So if we were to represent both of those on the same diagram, we would have something that looks like this here at the bottom. So in between the nuclei, okay, we'll highlight this in green. This is going to be our bonding MO in between them. And then the anti-bonding one are going to be on the outside like this. The anti-bonding is a result of destructive combination. The bonding MO is as a result of constructive combination. So because these MOs lie along the internuclear axis, right? And the internuclear axis, if you find the nuclei, the internuclear axis is just directly from one to the other, that dashed blue line between them. These MOs are known as sigma MOs, sigma molecular orbital. We saw the term sigma before when there was head-to-head or head-on overlap. It's the same idea here. We're going to have our sigma molecular orbitals. Okay, so now we can use a little bit of notation to try to differentiate between them. So because we combine in the case of hydrogen, this was a 1s from one hydrogen and 1s orbital from the other one. What we're going to have now are sigma subscript 1s bonding MOs or bonding MO. And then we're also going to have the anti-bonding MO, which we refer to as sigma star 1s. Okay, so the bonding one, again, results from the constructive combination. The anti-bonding, the sigma star results from a destructive combination of the atomic orbitals. These molecular orbitals are going to have energies associated with them. And what we're going to find is the following. So if I were to represent on an energy axis here, so energy increasing from bottom to top, and if I represent a 1s orbital maybe on this side from a hydrogen atom, this is the 1s orbital with one electron in it, and I have another hydrogen, say on the other side, over here with its 1s, right? They're equivalent in energy because they're both 1s orbitals, 1s1, 1s1. Like this, when these two atomic orbitals combine, we're going to get two molecular orbitals, right? These are, we'll refer to these as AO atomic orbitals. And then MO obviously is going to be our molecular orbitals that belong to the entire molecule. So we're starting off with these two atomic orbitals, the 1s orbitals. When they combine, they can combine constructively. So when they combine constructively, those that leads to the bonding molecular orbital. They tend to stabilize the molecule, and they're going to have lower energy. than the individual atomic orbitals. So we'll actually have a molecular orbital being formed that is going to be lower in energy, so maybe like around down here, than either of the atomic orbitals. And then we're also going to have the anti-bonding molecular orbitals that actually now destabilize the molecule, and those are going to be higher in energy than either of the isolated atomic orbitals, so they can be written or drawn above the level of either of the atomic orbitals. All right, so we have these two molecular orbitals that result. So we have our MO up here. We have another MO that's lower in energy, and we can label these now. Okay, the one that's lower in energy, that is the electrons in the bonding molecular orbital. So this is going to be now our sigma 1s MO. And we're going to have above it the ones that destabilize. The anti-bonding MO, this will be my sigma star 1s orbital. Now, because I put two atomic orbitals in, I get two molecular orbitals out. And now each of these atomic orbitals had an electron in them. So we have a total of two electrons putting in. I actually get those two electrons out. I'm going to stick those electrons in, just like I would populate any orbital diagram. I put them in starting with the lowest molecular orbital first. First electron goes in. I want to complete this MO before I move to anything higher up in energy. So that second one then gets paired up, right? We need to complete that energy level before you go to the one higher up. That's the Aufbau principle, the building up principle, right? So this would be a representation of the um, the combination of the atomic orbitals in H2 and hydrogen, where we have a bonding MO that's lower in energy than either of the atomic orbitals. We have the anti-bonding MO that's higher in energy than either of the atomic orbitals. We start populating the MOs with the lowest energies first, one at a time. We pair them up, we fill that energy level before we go to the next one higher up. So when we start looking at the electrons that we put into the bonding and the anti-bonding MOs, we can calculate something known as the bond order, which is an indication of how stable a molecule is going to be. Okay, we talked about stability being sort of the driving force for lots of things in chemistry. Okay, and that's going to be the same situation here. So the bond order will tell us how stable a particular molecule is. And again, stability is really the driving force for chemical reactions, chemical properties. And when we calculate the bond order, it's a very simple interpretation. The higher the value for the bond order, the more stable that molecule is. Okay, and the bond order is a simple calculation. What we're going to do is we're going to take the number of electrons in our bonding orbitals. We're going to subtract the number of electrons in the anti-bonding orbitals, and then whatever we get, we're going to divide that by 2. Okay, so if I go back up to the example that we just did with the hydrogen molecule, I can calculate the bond order, which it's not the best abbreviation, but bond order is often abbreviated BO for bond order. So the BO for H2, according to the molecular orbital theory, would be the number of electrons in the bonding orbitals, so that's this one here, that's 2, minus the number of electrons in the anti-bonding orbitals, which is 0. And I divide that by 2, so that's 2 over 2, which is 1. So we can predict the bond order of 1 that H2, okay, does exist, first of all, okay, and it is relatively stable. The bond order of 1. All right, so the higher the bond order, the more stable it is. The lower the bond order, the less stable it is. So we can take that, we can apply it now to even, larger combinations or combinations of larger things. So in the case of helium, right, we have two helium atoms. We try to combine those. Remember, helium has electron configuration 1s2. Okay, so I have my 1s2 electrons here. If I have one helium atom and another one, Again, I'm combining now two s orbitals. I'm going to get two molecular orbitals coming out of this. I'm going to have a bonding orbital down here, the sigma 1s, and the sigma star 1s. That's going to be the anti-bonding. I put a total of 2 into 4 electrons in. Okay, I'm going to get 4 electrons out. I'm going to put them into each of the molecular orbitals in order of increasing energy. So the first one goes in, I pair up with the second, and I go to the next energy level, put the third, and then the fourth. All right, so I've accounted for all of those 4 electrons that are in the He2 molecule. If I calculate the BO, the bond order, I take the number of electrons in the bonding orbital down here. That's 2. I subtract the number of electrons in the anti-bonding orbital, which is 2. I divide that by 2. 2 minus 2 is 0. 0 over 2 is 0. Bond order of 0 suggests that He2 does not exist. Right? So it's not stable at all. It's not going to exist as a result of that. So we can calculate bond orders based on our MO diagrams, right? So these are going to be our molecular orbital diagrams for the combination of the atomic orbitals. So we've talked about the formation of sigma molecular orbitals. What about the pi molecular orbitals? Well, the p atomic orbitals, these can also combine by constructive and destructive combination as well. We're going to get 2 types of molecular orbitals when we combine these as well. We're going to get sigma molecular orbitals, where again, the electron density is along the internuclear axis, right? So for example, if I have one, I'm going to see if we can make this work here. If I have one atom on this side with a set of p orbitals. Remember, the p orbitals are along the 3 axes, so 1, 2, and 3, like this. Okay, if I have another atom over here with, do this in a different color, with its 3 p orbitals as well, so 1, 2, and then 3, okay, what can happen is these 2 orbitals here, they can combine and they can produce an electron density that is going to be in between now or along the internuclear axis. So along this way is where that electron density is going to be the greatest. That's going to lead to a sigma molecular orbital along the internuclear axis. That's going to look something like this down here, right? That's where the electron density is the greatest. And in addition to that, we'll get the sigma star that are on the outside, these regions here. This will be our sigma, and this will be our sigma star on the outside. What can also happen, because that we have 2 other p orbitals now, these can produce molecular orbitals where um, they produce pi molecular orbitals where we have electron densities that are going to be above and below the internuclear axis, right? So you can think of now, again, your sort of banana bonds applied to MO now. We have an overlap that's going to be, or a combination here that's going to lead to electron density above and below the internuclear axis. And don't forget, we also have these that are going to overlap there as well, right? So the ones like this. So the remaining p orbitals can also combine in a similar way. So what we end up with are a set of molecular orbitals. We get, if we combine p orbitals, we get pi, and we also get 2, so we get sigma, and we get 2 pi molecular orbitals. And the sigma molecular orbital electron density is in between the internuclear, or along the internuclear axis. For the pi MOs, the electron density is above and below the internuclear axis. So the results that we have from that, from the combination of the p orbitals, again, are higher than those resulting from the combination of the s atomic orbitals in terms of their energies. So for instance, if I have a 2s and a 2p that I combine, their energies are going to be lower than the energies of the of the p molecular orbitals that result. Okay, and what we're going to see here is uh, it's possible in some cases for the s and p orbitals to mix, and in some cases the s orbitals will interact only with s orbitals, p orbitals interact only with p orbitals. And in this case, there's no mixing of the S and the P. And this is going to happen in instances where we're looking at oxygen, where we're looking at fluorine, where we're looking at neon. So there's no mixing here of the S and P orbitals. And as a result, the order of energies here is going to be as follows. We have our sigma 2s followed by the sigma star 2s. We have our sigma 2px. So this is going to be the electron density along the internuclear axis. And then the sigma star is 2p is going to be way up at the top. And then in between, we're going to have our pi 2py, pi 2pz, and then the pi star 2py, pi star 2pz as well. Remember, if you have a bonding one, you have to have an anti-bonding one that goes along with it as well. Right, so this order of the molecular orbitals in increasing energies like this assumes no mixing of the s and p orbitals. In some cases, the s and p orbitals do mix together, and what we're going to see is that the order of the orbital energies changes somewhat, and this occurs in instances of lithium, boron, carbon, nitrogen. So here we're going to have our sigma 2s, sigma star 2s at the bottom. And now instead of having the sigma 2px next, we actually have the pi 2py and pi 2pz, then the sigma 2px, and then we have the sigma star 2py, sigma star 2pz, and then the sigma 2px, sigma star 2px at the very top. Okay, so in a couple cases, so you'll see now the beginning of the second period, we have this mixing of the s and p orbitals, which leads to the sort of an anomalous order of the energies. And then later on in that period, the O, F, and N, E, further to the right on period 2, we have a different order of the energies that's for the molecular orbitals. So you want to keep that in mind when you start looking at these, either in ALEKS or in your homework assignments, the order in which they appear. So when we fill our MO diagrams, we're going to follow the same rules as filling the atomic orbitals. We actually look, at a simple example in the case of helium and hydrogen early on. But just to reiterate, we're going to fill the lower energy orbitals first, right? That's kind of similar to the Aufbau principle, the building up principle that we talked about way back when. We're also going to apply the Pauli exclusion principle. Okay, where each orbital can accommodate a maximum of 2 electrons with opposite spin. And then we're also going to follow Hund's rule, right? So if there are orbitals of equivalent energies, so these are degenerate orbitals, in other words. Okay, we're going to place 1 electron in each orbital before pairing up. Okay, and if you recall the sort of the analogy I used for that, when we talked about orbital diagrams for atoms, a few weeks ago, the bus seat rule, right? So you stick 1 in each seat before you start pairing them up. Okay, so if we take a look now at some of the examples, we're going to see the following. And specifically, I want to turn your attention to the oxygen, the O2 molecule that we have. Okay, so you will notice in all of these, these are all second row, second period homonuclear diatomic molecules. Again, homonuclear means that they're made up of the same atoms. Okay, in all of these in our MO diagrams, you don't see the 1s the sigma, rewrite that, the sigma 1s and the sigma star 1s, and that's because they are both going to be completely occupied with orbitals, and they're going to essentially cancel each other out. So we don't need to account for them in our MO diagram. So in all of these, you'll see they start with the sigma 2s as the first molecular orbital. So let's take a look at an example of the oxygen molecule, and we'll derive this one here just to illustrate the point. Okay, so I have my energy. Okay, and I have the oxygen atom on one side and another oxygen atom on the other side. And these are all going to now contribute. So oxygen, remember, is 1s2. We have 2s2, and then what is it, 2p4, right? So we have, in the case of the oxygen, both of these are going to have the same electron configuration. We can omit the 1s2, the core electron, for right now and focus on the valence electrons. So we have our 2s atomic orbital with 2 electrons in it. We have our 2p. Okay, 1, 2, and then we have 1, 2, 3, 4 electrons, right? Same thing with the oxygen on the right side. Okay, it's going to be identical to it. We're going to have our 2s with our 2 electrons in it, and then our 2p with 4 electrons. So 1, 2, 3, 4. So when we combine these, I should probably spread these out a little bit. So hang on a sec while I move them. Okay, so we spread them a little bit. So when I combine now these 2s atomic orbitals in both of these oxygens, we're going to get our resulting atomic orbital, I'm sorry, molecular orbitals. We're going to get a bonding one. So this is going to be my sigma 2s bonding orbital. I'm going to get an anti-bonding one that's higher in energy. Okay, this is going to be my sigma star 2s. So I put in 4 electrons. So I'm going to have 4 electrons to account for. So I put them in 1, pair it up 2, go up to the next one, 3, and then 4. All right. So when I combine now these, the 2p or atomic orbitals to give us our molecular orbitals, again, the molecular orbitals are going to be in green. I'm going to first of all get my sigma 2p. That's going to be lowest in energy out of the p orbitals. And I can go ahead and draw the sigma star now, 2p, that's going to be the highest in energy all the way up here. I'll list that to the side. And then I also have now the pi molecular orbital. So I have my bonding one that are listed first, and I have 2 of those. These are going to be equivalent in energy. So this is my pi. We have 2p, 2py, and the pi 2pz. This is 2px. And then I have my anti-bonding ones that are right above it, higher in energy. This is going to be the pi star, 2py, and then the pi star 2pz. Okay, so I'm putting in 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I'm going to stick those in according to the rules. So I put and start with the lowest out of these energies. So 1, paired up 2, and then 3. Make some room here. 3, 4, right, one at a time, then 5, 6, and then 7, and then 8. Remember Hund's rule, right? So those are all of the electrons accounted for in this O2 molecule, right? In the middle here in green, these are my MOs, my molecular orbitals that result from the combination of the atomic orbitals on the side. And when I look at this MO now, hopefully you can see in the case of oxygen, I have 2 unpaired electrons. And this now explains that observed phenomenon for oxygen where it is actually paramagnetic. So we have unpaired electrons in this that we couldn't tell from the Lewis structure or from the valence bond theory, we were not able to tell that there was unpaired electrons. Okay, so that makes this paramagnetic as a result. What we can also do is we can calculate the bond order for this. So our BO, the bond order, the number of electrons in the bonding orbital. So let's say we have 2, and 2 is 4. We have 5, 6, 7, 8. So 8 in the bonding orbitals minus the number of electrons in the anti-bonding orbitals. Let's say we have 2 here. Those are all the stars. 2, and then 3, and then 4. So 8 minus 4 divided by 2. 8 minus 4 is 4 divided by 2 would give 2 as our bond order. This tells us that oxygen O2 is actually very stable, and it does exist, and that's a good thing. There's oxygen molecules all around us that we need for a whole host of reasons and uses. Okay, so in the case of O2, we can use molecular orbital theory to explain a phenomenon that we would not be able to explain otherwise by using any of the other bonding theories. So if we were to look at some of a comparison between the different bonding theories, we'll see some strengths and weaknesses between them. Or for them, and we can compare them to the other bonding theories. So for instance, the Lewis theory's strength is that we're able to qualitatively predict bond strength and bond length. Now, again, this is just a qualitative prediction. It's not like any numbers associated with it. We can just compare things. Weaknesses, lots of weaknesses. It's a two-dimensional models, or it is a two-dimensional model. Whereas as we've seen, real molecules actually have significant three-dimensional nature to them. The Lewis theory doesn't really explain why bonds form in the first place. The VSEPR, which is an extension of the Lewis theory, helps us predict the shape of lots of molecules and polyatomic ions, but it also suffers from the same weakness as Lewis theory does, in which it fails to explain why bonds form in the first place. Valence bond theory, VB theory that we talked about, has a strength where it explains the formation of covalent bonds when there's the overlap of atomic orbitals. However, it still does fail to explain the bonding in several other types of molecules. The hybridization of the atomic orbitals, which again is an extension of the valence bond theory, it explains the bonding as well as the geometry of several more molecules. So it's a little bit more widespread in terms of its applicability or its application. But it does still fail to predict some of the other important characteristics, such as the paramagnetism or diamagnetism of certain molecules. We've just been able to see how MO theory can be used to predict that magnetic nature of certain molecules, and it can also be used to predict other properties of different molecules as well. The weakness of MO theory is that it is inherently complex. Okay, so it does involve several more steps. We're mixing, we're combining all of these atomic orbitals to make these molecular orbitals that belong to the entire molecule. So because it's so complex, we usually just reserve its use for situations where it is absolutely warranted. Where we can use simpler models to describe bonding, we will do that. Only where those models fail will we then invoke these more detailed models of bonding. So when we need to describe the bonding in different molecules, ideally what we'd like to do is use the simplest model to describe bonding where applicable. And then again, if we need more complex models, then we'd use those. In some cases, the bonding is described by using a combination of models. And a good example of this is in the case of benzene, which has the chemical formula C6H6. This can be represented when you draw the structure of benzene. We can draw the Lewis structure. So this is the Lewis structure. It can be represented using two resonance structures. So each of these points here is a carbon that's not shown. And to each of these carbons, there's also a hydrogen attached. That's just omitted for simplicity's sake. Okay. And this is one resonance structure that can be drawn. This is another one that's right next to it. And you can see the difference between them really is where the double bonds are located, right? So in the example on the left, the double bonds are in the top right, and then they alternate double, single, double, single, double, single all the way around. In the structure on the right, the double bonds in the top left, and again, it does alternate double, single, double, single, double, single all the way around. If you look at each of these carbons in the benzene ring, this is a ring structure, this one here, for example, you will see that there's a total of 3 electron groups around it. Okay, so 3 electron groups around. So we can then predict that this is going to be sp2 hybridized. Okay, which means that there is still a unhybridized p orbital that remains. So that's important because when you look at the structure of benzene and you look at the lengths of the bonds, for example, you may think, well, this carbon-carbon double bond here, right, should be shorter than the carbon-carbon single bond there. Shorter bond, single bond, shorter bond, single bond, etc. Actually, what you find is that all of these bonds are the same length. So why does that actually happen? Well, if you think about that unhybridized p orbital that is on each of these carbons in the ring, okay, so we have one, we'll do this in a different color, and we'll just use a structure on the right side to illustrate this point. So I have an unhybridized p orbital here, another one over here, another one on this one, another one over here, another one there, and then one at the top. Okay, as you can imagine now, there's overlap, there's side-to-side overlap over there. There's a side overlap at the top, there's side-to-side overlap here, side-to-side overlap, side-to-side overlap there, and side-to-side overlap. That's happening above the plane of the ring, but it's also happening beneath the plane of the ring as well. So there's side-to-side overlap happening in purple there, there's side-to-side overlap there, side-to-side there, side-to-side here, here, and there as well. So we're using both Lewis theory to explain the bonding. We're looking at, in this case, also valence bond theory and hybridization and orbital overlap to explain the fact that those pi bonds that form from the side-to-side overlap, okay, we end up with these pi bonds where we have double bonds, remember? And the side-to-side overlap of the unhybridized p orbitals, these are actually delocalized, meaning that they are spread out over the entire molecule. They're not just in one specific location. Instead, that structure is much more accurately represented like this one over here on the bottom, right? So we can put all that together and have a pi molecular orbital is being represented now all the way above the plane of the ring, and also beneath the plane of the benzene ring as well. Okay, so this is a good example of where we have a combination of the different bonding theories to describe what we observe in this case of benzene.